Hello, I'm Mr. Muskeluk, your AP Chemistry teacher at ChemAdvantage.
Well, here's a MC question on bond energy, and the bond energy questions are notoriously difficult, so let's see if we can solve it quickly and easily. We have hydrogen peroxide, which decomposes into water and oxygen. This is an exothermic reaction. It produces plenty of heat, and here's a short video of it. Well, that's a dramatic experiment, but let's get back to the problem. The change in enthalpy for this decomposition reaction has 2 moles of our peroxide. Here is our hydrogen peroxide, and here's the steam that it turns to, and they give us some data. The oxygen gas reaction is negative 196 kilojoules. We have the delta H of this reaction. You may assume the bond enthalpies of oxygen and hydrogen bonds in H2O are not significantly different from those in the peroxide bond. So these OHs right there are the same as reactants and products in terms of energy. Now they also give us the bond enthalpy. The bond enthalpy for the single bond oxygen, 148 kilojoules per mole. Our bond enthalpies are always positive. It's what's required to break a single OH bond. That's the 148 kilojoules. So we know the 148 kilojoules, and we know the overall delta H for the reaction, and they want the bond enthalpy for diatomic oxygen, this one. Well, first of all, we can see we have the single bond is 148. This is a double bond, so it's going to be more than that significantly. So immediately you can get rid of 2 of these answers. We know that it's not going to be less than 148, and it's not even going to be close to 148. So now you're down to 2 possible choices. 300 kilojoules, about double this, and 500, a bit more than that. Now, which one is going to be? I don't know. You could guess, but we can solve this pretty quickly without having to guess. Let's take this diagram again, this diagram that shows what's occurring in the reaction, where we have the 2 peroxides turning into water and our oxygen that's released. This makes double bonded oxygen for us. We know in a reaction in terms of bonds, we've got to break these bonds up so that they're just oxygens and hydrogens, and then reform them into water and our oxygen with this double bond. But they give us a hint here saying that the oxygen-hydrogen bonds, these OHs, are not different from our reactant to our product. So to simplify things, we could simply take and say, well, this OH bond hasn't changed. It's the same before and after. So I'm going to get rid of this water and bond that we have and do the same for this one, because this OH before and after are the same. And of course the same applies here for other peroxide. I can just do some more elimination and simplification of the reaction where that is the same, so there's be no change in that part of the reaction, and the same goes for this. And see what we have left over. We've found that all we have to worry about is breaking these bonds, the single bond oxygen, so we get the 2 O's. That's going to be an investment of, they tell us what this bond energy is, 148 kilojoules. So we got to break 148, 148. Then we have our 2 O's, and then remake this. And when we remake this, we get a total of 196 back. So our investment is 2 times this 148 kilojoules. That's our investment. We put that endothermic in, and we get exothermic back 196 kilojoules. Well, if you're good at your math, you can probably see what the answer is now, but let's do it mathematically. Let's solve this as a problem where we just simply take our reactants and our products, and this is the equation, of course, the equation that we've learned is the change in reaction, this negative 196 for this overall reaction, is equal to the addition of the bond energy of the reactants. We break these guys and make these, and that's why we have the negative sign. So we can put the numbers in if you like to do it mathematically. We can say, okay, we have result of negative 196 kilojoules. Negative 200 kilojoules are made. That was the steam and heat that we saw from the reaction. But to do that, we break up two of these oxygen bonds, and we end up getting this result. The negative sign lets us get that result. This is the only reaction where we've got the reactants before the products, but that's because we have delta H here and we have bond energy here. Well, the math is going to be easy. You got a calculator now with the multiple choice exam, so we can just go and put these numbers in. 2 times 148, 296. This is now algebra. That's very, very solvable. You don't even have to use reasoning, though you should understand what's happening, and say, okay, the result is negative 492, and of course a negative, that's here. You follow your algebra, and our bond energy, therefore, from this data for a double bond oxygen is 492 kilojoules, and hey, we've got that possibility here. So we've solved it both in terms of understanding what's happening, breaking these two, investing 296 kilojoules, getting back negative 200 kilojoules. So we know we've got our final answer where the formation of this double bond produces a lot of energy.